we are going to discuss in this class simply supported beam with overhang or an overhanging beam. See, simply supported beam AB and BC is the overhanging portion, overhanging to the right of B. It carries uniformly distributed load 2 kilonewton per meter over the 6 meter length, and there is a point load or a concentrated load of 2 kilonewton at the free end C. So to draw the shear force diagram and bending moment diagram, always the first step is find the reactions RA and RB. Okay, so find RA and RB. Here I have taken the total load 2 kilonewton per meter acting over a length of 6 meter. Take moment about A. I'm taking moment about A so that this 2 into 6, or I have taken this 2 into 4 separately. First 2 into 4, it is acting at 2 meter. So 2 into 4 into 2 clockwise moment. This 2 into 2, this much portion, 2 into 2 acting at, this is 1 plus 4, 5. So this is the total moment of this UDL. Instead of this, we can write it in one single step. The load is 2 into total distance is 6. 2 into 6. And it is acting at the center of it. So 2 into 6 into 3. So that will be 12 into 3, 36. That same value will get in if you split also. Here I have written it split up. 2 into 4 into 2, 16. 2 into 2 into 5. So it is 20. 20 plus 16, 36. So either you can write it as split up as this load plus this load, or even if you take it as the whole load, it will be the same. Hope it is clear. So I am taking this entire load 2 kilonewton per meter acting over a distance 6 meter, that into half the distance of 6, 3, 36, this much value written within the bracket. Then this 2, moment about this point. So vertical load 2 into distance 6, 6, that is written here. 2 into 6, that is also clockwise. Then this reaction RB. RB produces an anti-clockwise moment. This produces anti-clockwise moment. So minus RB into 4. Minus RB into 4 is equal to 0. From that you got RB is equal to 12 kilonewton. So first step is we have got RB. Or as we have done earlier, if you want, you can do it in another way also. I will write that step here. See, if you want to find RA first, what you have to do is, even as we have done earlier, you can take RA into 4 clockwise. You can write RA into 4 clockwise. Okay. Then this 2, this much portion load, 2 into 4, isn't it? Up to the left of this load is 2 into 4, acting at distance 2, that will produce anti-clockwise moment. So 2 into 4, the load is 8, acting at a distance 2 meter, produces anti-clockwise moment because it produces anti-clockwise. Now, coming to the right of B, this load, 2 into 2, 4, acting at a distance 1 meter. So that load will produce, this load about B, it will produce clockwise moment. So plus the load 2 into 2 acting at a distance 1 meter. Then this load 2 kilonewton acting at 2 meter, that also produces clockwise. So 2 into 2 is equal to 0. So if you take moment about B of all the forces and equate it to 0, you can get RA first. This RA will be obtained first. What is the value? 2 into 2, 4. This 2 into 2 is another 4. 4 plus 4, 8. This is minus 16. Minus 16 plus 8 is minus 8. It goes to the right side. So we will get RA is equal to, we'll get RA as 8
We'll get Ra is equal to 8 by 4 is equal to 2. Here also we have got initially Rb 12, then Ra plus Rb is equal to total load 2 into 6, 12 plus 2. So 12 plus 2, 14. So we'll got Ra is equal to 14 minus 12, 2. Here also we get Ra is equal to 2. Okay, so you can either take moment about B and get Ra first, or you can take moment about A and get RB first. Either way is correct. As we have done here, we have taken moment about A. So we have taken the total loads, moment about A. All these loads will produce clockwise moment. So that is written first. And this RB will produce anti-clockwise moment. So that is written here. Is equal to 0. From that we get RB is equal to 12. Then RA plus RB is equal to 2 into 6 total load plus 2. So 14. From that we get RA and RB. So either you can take moment about A, get RB, then use vertical equilibrium and get RA. Okay, so you have to find RA and RB correctly. Once you get RA and RB, mark it here to 12. Now, now we can easily write. There is no need for any help from FA. Shear force at A is 2. Draw a line 2 kilonewton. Shear force just to the left at point B, there is a vertical load 12 kilonewton acting upward. So just to the left of B, RA is upwards, minus 2 into 4, 8. So 2 minus 8, it is minus 6. So mark minus 6 at point B, minus 6 units downwards. Since UDL, connect it with a straight line. So 2 upwards, you have marked 2 upwards. Suddenly decrease to 8 units decrease, so you come to 6. Then at the point B, just to the right of it, this minus 6 plus 12. So FA is equal to 2. FB left is equal to 2 minus 8 minus 6. FB right is equal to minus 6 plus this 12 plus 6. So at this point, you mark plus 6. Then in this portion, just to the left of C, see there's a vertical load. So just to the left of C, up to here we have reached 6. 6 minus 4. 6 minus 2 into 2. 6 minus 4, it is equal to 2. So you mark 2 kilonewton. Since UDL connects 6 and 2 by a straight line. So this is, you have returned each step. FA equals to FB left, FB right, and FC left. Even otherwise, we can easily draw it. See, there is a vertical load to draw the baseline. From the baseline, you go 2 kilonewton up. You have gone 2 kilonewton up. Then straight UDL. So come down by 8 units. From the 2, you come down by 8 units. So you reach minus 6 here. Then there is a load 12. So you go up by 12. So minus 6 plus 12, you will get 6 kilonewton. You have gone up. There is another decrease by 4. So from 6, you decrease by 4, you reach 2. At that point, there is a vertical load 2 downwards. So from 2 downwards, you reach C. So start from the baseline, go up by 8, again go up by 12, go down by 4, come down. So this is how the shear force diagram is drawn. Now, one thing you have to note in the case of an overhanging beam is, here the shear force is going from one side to the other side. There's a change in the shear force, or shear force becomes 0 at this particular point D. That point is very, very important, because at that point, the bending moment will be a maximum. Where shear force is 0, bending moment is maximum. So I have to locate this point D. So once you draw the shear force, then itself you find out the point of 0 shear force. Point of 0 shear force, this is two similar triangles. Let it be at a distance x from one end. That this point is x from A. So we can write 2 divided by x is equal to, this is 6. 6 divided by this distance. This distance is, the span is 4. So this distance is 4 minus x. This distance is 4 minus x. So 2 by x is equal to 6 by 4 minus x. You write here 2 by x is equal to 6 by 4 minus x. Cross multiplication. 8 minus 2x is equal to 6x. From that, we get x is equal to 1 meter. So the point of zero shear force has to be located. That is very, very important. So you marked it 1 meter. Okay, then only the shear force diagram will be complete. Now coming to bending moment, here MA is equal to 0. In the overhanging beam, MB is not 0. MA is 0, and the moment at this free end, at the end C is 0. Okay, so we can first write MA is equal to 0. Then coming to this point B, coming to point B, moment is RA into 4 clockwise. So left of section clockwise positive. So RA into 4, 2 into 4, 8. Then this load, 2 into 4, acting at the center of it. 2 into 4 acting at 2 meters. That is anti-clockwise. So moment at B is equal to, I can write, minus RB can be written, MB can be written as RA into 2. RA is 2. RA into 4. 2 into 4. I'll write it once again here. MB is equal to 2 into 4 clockwise minus this much load. 2 into 4, 8. That 8 acting at 2 meter. So 8 into 2, that is anti-clockwise. Okay, how much it works out to? 8 minus 16, it works out to minus 8. So this is found out in another way also. So as usual, we can take MB is equal to 2 into 4 minus 8 into 2. In this case, we can also consider when there are several loads, you can consider moment at B can be considered from the right side also. If you consider from the right of section, that will be this vertical load 2 into 2. That is a clockwise moment. Right of section, you have the sign convention is left of section clockwise positive, right of section anti-clockwise positive. So this 2 into 2, that is clockwise, so it is minus. And this 2 into 2 UDL acting at 1, that is also produces clockwise anti-clock. So that is written from considering the right of section, I have written here minus 2 into 2 plus 2 into 2 into 1. It is also minus 8. So you can do any of this way. It is better you consider from left. Consider from left RA into 4 minus 2 into 4 into 2. In that way also we'll get minus 8. So bending moment at B is minus 8. And bending moment at C, it is the free end. It is equal to 0. So you have to draw the diagram. I have MA 0 and I have got MB as minus 8. So from the point D, you mark minus 8. Since it is a parabola, you have to connect this minus 8 and this 0 by a parabola. But remember, this point, the moment is going to be maximum, where there is zero shear force. So I have to connect this point and this point using a parabola. And this is going to be a maximum value. I don't know whether this maximum is positive or negative. So only after calculating that value, we can draw the bending moment diagram. Okay. So I'm going to calculate the maximum bending moment value. Maximum bending moment value will be at the point where the shear force is 0. So the point of 0 shear force is marked here as D. So how will you find out the moment at D? That point D, you can produce it here. 1 meter. At 1 meter from here, RA into 1 clockwise minus this load 2 into 1 acting at 1 by 2 or 0.5. So maximum bending moment is 2 into 1 minus the load 2 into 1 into 0.5, will get 1 kilonewton meter. It is positive. So at this point, you mark at the point D 1 unit upward. At the point B, 8 unit downwards. And you have to connect it with a parabola like this. Convexity upwards. Convexity upwards. Now here the moment is 0. Connect this and this so that the convexity upwards. That is this shape. So this is the bending moment diagram for an overhanging beam. It will be having positive moment as well as negative moment at the support. Now, since the bending moment diagram crosses this baseline, there is a point where the bending moment happens to be zero. A point where the bending moment is zero, and that point is called the point of contraflexion. The point where the bending moment is zero is called the point of contraflexion. How to locate this? You write down this is the point E. This point E can produce it upwards. I'll remove all these previous markings. So this point E, you produce it. Say this is be corresponding to this point E. So this is point E here. Consider left of it. Take Write down the expression for bending moment at T. Let this be at a distance. What I have written here. Let me see what is the distance I have written. Point of contraflexion. Say at a distance x from A. So at a distance x from A, what is the moment? This 2 into x. This distance is x. So RA into x clockwise. This much load, 2 into x, acting at x by 2. So I have written RA into x minus 2 into x by 2. So 2x square by 2 is equal to 0. So we'll get 2x minus x square is equal to 0. Taking x outside, x into 2 minus x is equal to 0. So either x is equal to 0, that is 1 point. At x is equal to 0, it is when you want to 0. And the next is x is equal to 2 meter. So at a distance of 2 meter from here, the bending moment becomes 0. So at 1 meter from here, bending moment is maximum. At 2 meter from the left end, the bending moment is 0. So it is very, very important. You are asked to draw the bending moment diagram and salient points. Mark the salient points. So you have to locate 0 shear force and maximum bending moment. And the point where the bending moment is 0 is called point of contraflexion. Okay. So this is the bending moment diagram. With that, we stop for the day. Thank you.